Hi everyone, thank you for joining us today for an NVM Express hosted webinar. Today we will be presenting NVMe 2.0 specifications, fast, simple, and optimized for the future of storage. Our presenters will provide an overview of the exciting new features and command sets in the NVMe 2.0 specifications release. Today we're joined by Peter Onufryk, Intel Fellow, Nick Adams, Principal Software Engineer at Intel, Matthias Bjorling, Director at Western Digital, and Bill Martin, SSD I/O Standards at Samsung. And to begin, Peter will start us off with a brief history of the evolution of NVMe technology.
Great, thank you for that introduction. Unlike previous storage technologies where there was one technology for servers, another for client, and yet another for mobile, NVMe technology is used across storage applications. We see NVMe technology used today in everything from cell phones and tablets to client laptops and desktops, all the way to storage arrays and data center. In the table on the right shows the unit growth for NVMe, and you can see the NVMe has grown from an emerging technology in 2016 to a mainstream technology in 2021. In 2021, we expect over 7 million units shipped into enterprise applications, over 20 million units shipped into cloud applications, and over 350 million units shipped into client applications. The NVMe architecture has been called the new language of storage since we're now seeing many people designing their systems around NVMe technology. Although NVMe has evolved into much more than we ever imagined when we started, our initial goal in creating NVMe was to create a standard interface for PCIe SSDs. We wanted the same experience with PCIe SSDs as one had with hard drives, where you just plug it in and it works. As you can see from this chart, in 2021, more NVMe SSDs will ship than all other SSDs combined, and the dominance of NVMe is projected to grow. So with that introduction to where NVMe is today, let me turn it over to Nick to describe NVMe evolution and specification refactoring.
Hello. So as we have grown with NVMe, the focus of the organization has really shifted. When we initially set out to define the NVMe architecture and the NVM command set, the goal was really around establishing a unified direction for PCIe SSDs with a common interface, a single way of interacting with those SSDs. We wanted to really focus on getting an inbox driver, as Peter mentioned, that same experience that was available for hard drives. So you just put it into the system and it worked when you started up. As that goal was accomplished, there was really a change in focus from a specification standpoint to look at what was required to be able to scale out the NVMe architecture to different types of use cases and different usage models. You know, one of the key pieces of that was focusing on being able to get our commands over an arbitrary fabric. So instead of just PCIe, expanding to Ethernet and to fiber channel. As those goals were accomplished, we've now moved into yet another focus of the organization. And that's really around innovation, but making it so that we can have new types of command sets and different usage models that are even beyond those original ones. But we want to do that in a way that doesn't interfere with or disrupt the large and vast number of SSDs that are out there in the ecosystem today. We really want to be able to provide an expanded set of use cases, but do that in a way that will just be smooth and allow us to grow. And so with that, that has taken us to really looking at what are we doing from a specification standpoint. As we started with NVMe, 1.0 and through 1.4, we had the NVMe base specification. We had a management interface specification, and as we talked about a minute ago, we added that NVMe over Fabric specification. But one of the things that we came to find out is that as we wanted to add more command sets and as we needed to be able to make distinctions for the different transports, the structure of our specification was kind of limiting the way that we were getting work done. And it wasn't representing necessarily the architecture that we were looking for within the NVMe spec itself. And so in order to kind of ease the development of NVMe-based technology, to enable some of that innovation that we were looking to see, we wanted to create an extensible specification infrastructure that actually allowed us to have that growth while making sure that we were able to really solidify and reduce the amount of change that was going into the actual support for that standard SSD. And so, with that, we kind of moved to a different model, one where we have our base specification, and that includes anything that is common for, kind of across these transports and across these different types of command sets. Then we created different command set specifications to be able to have definitions for how the operating system or the host interacted with each of the different types of command sets, whether that be the NVM command set, which has been there since the beginning of NVMe, or the newly defined zone namespaces command set, or the NVMe key value command set. Additionally, we went and made our transports very, separated out that transport. So even the PCIe transport definition that had been there since the beginning, we pulled that out to its own specification. We also have the RDMA transport specification and the TCP transport specification, again, making it so that the transport is abstracted from the actual base of the NVMe definition. And with that, we actually have kept the NVMe management interface specification consistent with how it was previously. With that, I'm going to hand this back to Peter so that he can talk about some of our NVMe 2.0 features.
Thanks, Nick. The first NVMe 2.0 feature I'd like to talk about is command group control. We added a new lockdown admin command to NVMe that may be used to prohibit the execution of a command or modify a feature. The lockdown command can be used to prohibit execution of an admin command, a set feature that modifies a specific feature identifier, or an NVMe management interface command. With the lockdown command, one can also control the interface on which the command is prohibited. The command could be prohibited in band on an admin queue, out of band through a management interface, or both in band and out of band. When a command is locked down or prohibited, it is prohibited until a power cycle or explicitly re-enabled using the lockdown command. Another new feature in NVMe 2.0 is the addition of a copy command to the NVM and zone namespaces I/O command sets. The command is simple. It allows you to copy one or more non-contiguous LBA ranges to a contiguous LBA range in the same namespace without transferring data through the host. This operation is useful for things like host-based FTLs. So before this command, in order to perform a copy, the host had to read the data into host memory with an IO read command, and then write the data back to a namespace using an IO write command. The new copy command allows you to do that in one operation without transferring data through the host. This saves host memory bandwidth, interconnect bandwidth, and reduces latency. When many of you think of NVMe, you think of a PCIe SSD. However, the NVMe architecture is now the new language of storage and is being used to construct warehouse-scale storage systems. Many of these warehouse-scale storage systems are represented by a single NVM subsystem. Up to this point, an NVM subsystem was a monolithic thing with controllers and namespaces. In an NVMe SSD, it's typically implemented by an ASIC with some NAND. But in warehouse-scale storage systems, it consists of many refrigerator-sized racks. These racks fail and need to be replaced. Sometimes racks need to be added to expand capacity. In other cases, the firmware associated with a rack needs to be updated. What we've done in NVMe 2.0 is defined how an NVM subsystem may be partitioned into multiple domains. Domains are a new architectural element in the NVMe architecture. A domain may contain capacity, controllers, ports, and communicate with other domains. In the NVMe 2.0 base specification, we defined how domains may be added, removed, reconfigured, or partitioned. This includes things like how reservations are handled when an NVM subsystem that was partitioned is unified. We also defined how an NVM subsystem signals a domain change to a host. Another new feature in NVMe 2.0 are enhancements in the way protection information works. Since we wanted NVMe to work across storage applications and protection information was required in many enterprise applications, we supported protection information from the beginning in NVMe 1.0. To maintain compatibility with other storage architectures, we use the same format as protection information in T10. As shown in the upper left of this slide, there's a 16-bit guard, a 16-bit application tag, and a 32-bit reference tag. Since a 16-bit guard is viewed as insufficient for large logical blocks, the first change we made in NVMe 2.0 to protection information was to add support for a 32-bit guard and a 64-bit guard. You can see the format of the 32-bit guard protection information in the middle and the 64-bit guard on the right. The second change we made was to add support for a storage tag in addition to a reference tag. The storage tag is an opaque data field not interpreted by the controller. During protection information checking, the value of the storage tag is compared to a value provided in the command. Since the size and use of the storage tag and reference tag varied per application, we added a storage and reference space field in the protection information so that one could configure how many bits one wanted to allocate from this field for the storage tag and how many bits one wanted to allocate for the reference tag. Some applications may want a large reference tag, other applications may want a large storage tag, yet other applications may want to split this field into a storage tag and reference tag. The figure in the lower middle of this slide shows how this works. When you split the storage and reference space field, the upper bits become the storage tag and the lower bits become the reference tag. In NVMe 1.4, we added endurance groups and media units as an architectural element to the NVMe architecture. Before NVMe 1.4, we had namespaces that could be in NVM sets. In NVMe 1.4, we allowed NVM sets to be in an endurance group. An endurance group is a portion of NVM in an NVM subsystem whose endurance can be managed as a collection. In NVMe 1.4, we also added media units that can be used to construct endurance group. A media unit represents a component of underlying media in an NVM subsystem. All of this was great, but we didn't have a mechanism to configure any of this. The idea was that it came pre-configured from the factory. This is common in the way we do things in NVMe. We start simple and then we add things later as they're needed. Well, in NVMe 2.0, we added the ability to configure all of this. We added a new capacity management command to the admin command set. And with this command, you can create and delete NVM sets, create and delete endurance groups, allocate media units to endurance groups, and allocate media units to NVM sets. Turning our attention to fabrics, NVMe 2.0 adds NVMe over fabric security features. NVMe over TCP previously supported Transport Layer Security, or TLS version 1.2. TLS 1.2 was released in 2008 and was considered fairly secure, but vulnerabilities have been discovered that call the security of TLS 1.2 into question. For this reason, we're moving NVMe to TLS 1.3. Starting with NVMe 2.0, all NVMe over TCP implementations that implement TLS are now required to support TLS 1.3. NVMe 2.0 will still allow TLS 1.2 as legacy, but everyone's strongly encouraged to move to TLS 1.3. Another security feature we added was a mutual host and NVM subsystem in-band authentication protocol based on Diffie-Hellman HMAC CHAP. This allows a host and an NVM subsystem to authenticate each other and make sure they're talking to who they think they're talking to. NVMe 2.0 added support for rotational media such as hard drives. I never thought I'd see this day, but as NVMe has become the new language of storage, people are architecting their systems around NVMe natively and want to be able to plug in hard drives into these systems. So we added support for hard drives to NVMe 2.0. Enhancements for rotational media include an indication that an endurance group and associated namespaces store data on rotational media, a log page that describes the rotational media. It includes things such as the number of actuators, rotational speed, and so on. Finally, since spinning up a hard drive can consume lots of power, we added spin-up control. One of the big things we did in NVMe 2.0 was redefine how multiple I/O command sets are handled in NVMe. NVMe had support for multiple command sets from the beginning, but it's important to note that while we had the foundation for multiple command sets since the beginning of NVMe, we were missing a lot of the key pieces required to actually implement multiple command sets. This was due to the fact that we only supported one command set, the NVM command set. In NVMe 2.0, we defined a new mechanism for supporting up to 64 I/O command sets, defined all the pieces necessary to actually support multiple command sets, and defined two new command sets, the zone namespace command set and the key value command set. Matthias and Bill will describe these later. So let's take a look at how this works. Associated with each namespace is now a command set. An NVM subsystem may support namespaces associated with different command sets at the same time, and you can mix and match attaching them to controllers in an arbitrary manner. On this slide, we have an NVM subsystem with 4 controllers and 9 namespaces. 4 of the namespaces support command set number 1, shown in green. 4 of the namespaces support command set number 2, shown in blue. And 1 namespace supports command set number 3, shown in purple. As this figure illustrates, you can have a controller that has all namespaces associated with one command set. This effectively means that that controller can only use that one command set at that point in time. This is true for controllers 0 and 1 on this slide. Controller 0 only supports command set number 2, and controller 1 only supports command set number 2. Or you can have a controller that has namespaces attached with different command sets. This is true for controllers 2 and 3. When this occurs, the host can issue commands from different command sets that target these namespaces, and the commands can be interleaved in an arbitrary manner. So there's no notion of a controller being in a command set mode. You can issue a command from command set number 1 to one namespace and immediately follow it by a command associated with command set number 2 to another namespace. If you're building an NVM subsystem, you may want to support multiple command sets, but you may not want to allow all the command sets from different commands to be interleaved in an arbitrary manner, since your use case may not actually require this, and supporting this arbitrary interleaving increases your implementation and validation complexity. To allow this restriction, we've created the Identify I/O command set data structure that contains multiple command set combinations. Each command set combination is a bit vector with a bit per command set, which allows you to select a subset of command sets that may be enabled by a controller at a point in time. This restricts the interleaving of command sets associated with different commands set by the controller. Using the I/O command set profile feature, the host selects the command set combination that it wants to enable on a controller. This allows you to control implementation complexity. It allows you to do things like the following. At one extreme, you can say, I want to support I/O commands, command sets 1, 2, and 3 on my controller, but I only want to allow one at a time. At the other extreme, you can say, I want to support all 3 command sets enabled at the same time with commands interleaved in an arbitrary manner. You can also do things in between. For example, you can express that you're allowing the enabling of command set 1 and 3 at the same time, or you can enable command set 2, but you can't enable all 3 at the same time. So with that introduction to multiple command sets, let me turn it over to Matthias to describe the zone namespace command set.
Thank you. All right, so this is it's a new command set that's part of the NVMe 2.0 specifications. The goal of this command set is to kind of eliminate the indirection tags that exists within conventional SSDs. I mean, and all general SSDs today. And it kind of represents a new division of functionality between the host and the SSDs. The benefits of these drives that implement this command set is that for many implementations, you can access get access to the full NAND capacity in the device, which could result in up to like 25% higher usable capacity compared to a conventional SSD. It also allows like higher endurance, where ZNS SSDs you can endure like 3.5 drive write per day, compared to like 2 or 0.8 for typical conventional SSDs. And it does that while also offering higher throughput and better latency quality of service. You can see over here to the right, this is a test case where writing to the drive as fast as possible. And there's DNS drive and 2 SSDs, one with 7% overvisioning, another one with 28% overvisioning. And they're both started from a clean slate when you start writing to them. And in the beginning, they have the same performance, but where the text starts to kick in, it means the garbage collection within the SSD process kicks in, the performance starts to lower for a conventional SSD. And whereas on a ZNS drive, it continues to be consistent. So to enable that, it's obviously isn't free. It is kind of, we are redefining where the division of functionality. So to do that and to achieve this, logical blocks are grouped into zones, and each zone has a zone type which defines its read-write access rules. And in the current revision of the ZNS command set, there is one zone type called sequential write required zone type, which requires the logical blocks are written sequentially within a zone, and that a zone must be explicitly reset. So what this means in practice is that the host for each zone with this particular zone type on the host will have to kind of write sequentially into it. Whereas on a conventional drive, you do have the benefits that you can actually do random writes to any LPA on the SSD. But by putting this requirement up to the host, you can kind of eliminate this tax, you can call it, that is, traditionally like a kind of is happening within a conventional drive. Given that this is and requires the host to engage with these types of drives, there is support required in the host, and there's a lot of ecosystem work being done in the communities around specifically Linux, but also other proprietary systems. Where for Linux, there's support from the Linux kernel and SPDK. There's file system support, F2FS, Btrfs. There are IO-intensive applications, RocksDB, MySQL, typically databases that have log-structured merge trees as their like data structure implementation are really good for this type of SSDs. There's a large breadth of libraries like something called libcbd, which you use to kind of access the easier program towards a ZNS SSD. There's libNVMe, NVMe CLI, and a lot of other tools that are kind of enabling support for these new types of drives. So there are a lot of benefits to having a random block interface, especially that we over decades have written software towards that kind of interface. So these particular SSDs are targeted to large-scale data centers, all flash arrays, high-performance computing, and more. And especially cases where you want to drive higher IOPS with lower quality of service, so high performance, and you want more consistent latencies, it's good candidates. For example, here to the right, we have MySQL, where you can do 3 times higher transactions throughput, while also having 6 times lower latency compared to conventional SD in specifically mixed or write-heavy MySQL use cases. Another place where ZNS also offers benefits are in extending like QLC. Due to having this higher drive write per day, it does enable previously previous use cases that previously wasn't good candidates for QLC, maybe to be considered. So it's also kind of enabler for that. And besides that, there's also this that you get more capacity depending on how much over-provisioning that is kind of that you traditionally use with your conventional drives, being at 7% or 28, which for ZNS drive in typical implementations is around 0%. Right. With that, I would like to throw the ball over to Bill. Go ahead, Bill. Thanks.
So I'd like to talk about the third command set that now is supported by NVMe 2.0. This is the key value command set. And first, like ZNS, this takes a major change in how data is stored, but it takes a different direction than ZNS in the fact that instead of block storage, which ZNS still supports and NVM Command Set still supports, this is key value storage. And so first I'd like to talk about what the differences are between block storage and key value storage. So in block storage, data is stored in blocks of a fixed size. So every block of data that you store is a certain fixed size that's defined by the format of your device. In key value, the data is stored as unstructured data. It can be anything from 1 byte long to a very large size. And we'll talk about sizes and all of that a little bit later. Secondly, in block storage, the data is addressed by a logical block address, which is a fixed size address. In key value, the data is addressed by a key. So the logical block address is a fixed number of bytes. Again, that's defined by the protocol. In key value, the key is variable length. We will talk about some of the restrictions on it, but for the initial key value storage that is currently defined in NVMe 2.0, that key size is anything up to 32 bytes in length. In block storage, storage space is allocated in integer multiples of block size. In key value, your storage space is allocated in increments of bytes. So again, you can have a 1 byte, you can have a 25 byte value that you associate with. In block storage, logical blocks are associated 1-to-1 with physical blocks, while in key value, the value is associated with an amount of physical storage necessary. So what are the benefits of key value? Well, key value is of significant benefit in data center applications, things like Ceph, RocksDB, which store things in essence as a key and a value. These are object storage protocols where your value is your object, and you're storing an object based on some identifier that identifies that object. So in the current logical block system on the left, once you get to a key value API that defines how the key is associated with your value or your object, you then, in a traditional block storage device, have to have a software key value store in your system, in your host, and in that you store an index and a log for that. You go through a POSIX API to get to the file system that does a block map of your index to a series of blocks, and you have a journal for that. And you finally get to a block interface. The block interface goes through the block device driver, and finally at the bottom gets down to your physical device. At your physical device, you now have the physical device command protocol that has a map from your logical block address to your physical block address. So in this, you've done 3 different mappings of your key to your value, and you have then broken your value or your data up into 1 or more logical blocks that are part of that mapping through the system. Now, with the key value interface, again, you come down to the same key value API, but now there's a very thin library that translates your API into key value commands for the device directly. You don't do any of the mapping. By doing this, you have increased your transactions per second and you have decreased your latency. So it comes down to the key value interface instead of a block interface that has a key value device driver as opposed to a block device driver. It finally gets down to the device, and you have one and only one mapping file that now maps from your key to the physical location on your device of where that value is stored. So you have reduced system overhead in terms of processing, and you have reduced system overhead in terms of storage of information. So those are the benefits of key value. Next, I'd like to talk about the constructs that we have. So the key is specified in the command. It is a 32-byte maximum length. It is a 1-byte minimum length and 1-byte granularity. So you can have a 1-byte key, a 2-byte key, a 26-byte key. You cannot have a 9-bit key. So the length of the key is specified in the command, so you know how much of that key to use. The length that is specified allows 255 bytes, while the command itself only supports 32. This is for future extensibility. So an N-byte key does not match an M-byte key. And what we mean by that is if you have a key that is 00 Baker Echo, that does not match a key that is just Baker Echo. Or in other words, if you have said, I have a 2-byte key, that cannot possibly match to a 1-byte key. For the value, again, the length is specified in the command. The command allows up to a 4 gigabyte value. One other key feature is that your value may actually be 0 length. This allows you to do a store of a key to simply identify that the key is there without having any data associated with it. So finally, what are the new commands? Because this is a new command set, you don't use the traditional read and write commands of a block storage command system. We have defined 4 new commands specifically for use with key value. The store command provides a mechanism to store a key value pair, much like a write command in a block system. The retrieve command provides a mechanism to retrieve that key value pair, again, much like a read command in a block storage system. The next command does not have an equivalent. It is the exist command. And this provides a mechanism to determine if a particular key value pair exists. So with this, you pass a key. You ask, does this key exist? And then you get a response of either it does or does not exist within the storage system. And finally, there is a list command. The list command provides a mechanism to list the key value pairs that are on a device. This is useful because in a traditional logical block or block addressed system, you could just walk through the blocks if you need to make a duplicate, a recovery, or what have you. And you could walk through all possible blocks and copy those wherever you want to copy them. And you can take a logical block address, a very long length, and get all of the data that happens to be stored in a large number of logical blocks. In a key value system, you can't walk all bits of potential key value pairs, especially when you consider that a 1-byte key is not the same as a 2-byte key where the upper bits are all zeroed. So this provides a mechanism to list the pairs that are on the device so that you could then potentially copy a device that you need to replace. So that's kind of an overview of the key value command set. And I'd like to pass it back to Peter to give you an overview of all that we've been covering.
Thanks, Bill. In summary, NVMe has become the new language of storage and is now being used in everything from mobile devices and simple PCIe SSDs to warehouse scale storage arrays. We now support every major transport and are shifting our focus to new innovations enabled by NVM and new use cases. The NVMe 2.0 specifications are all about refactoring. We refactor the specifications to ease development of NVMe-based technology, enable rapid innovation by minimizing change to specifications associated with broadly deployed solutions, and create an extensible specification structure that will enable the next phase of growth for NVMe. The NVMe technical community continues to accelerate technical development by maintaining existing specifications and extending them with new features and innovations. In this presentation, we've given you an overview of NVMe 2.0. NVMe 2.0 is all about refactoring, but we've added new features and new command sets that we've given you an overview today about. I encourage you to go to the NVM Express website and download the specifications for more detail. Thank you.
Great, thank you, Peter. Thank you all for providing your professional expertise. Now we'd like to open up the webinar for a live Q&A. So if you have any questions for our presenters, please submit them and we will do our best to answer them here. So for question 1, how many command sets did NVMe support before NVMe 2.0?
I'll take that one. So there are actually kind of 2 answers to this question. There's actually an admin command set and IO command set. So when we talk about supporting multiple command sets, what we're really referring to is supporting IO command sets. And although we had support for multiple command sets in NVMe 1.0, we only had one command set, the NVM command set. That was the only IO command set. That's what all of you know as the traditional block storage command set of NVMe.
Great, thank you for that answer. For the next question, how did you come up with the spec partitioning that was used?
Sure, this is Nick and I can take that question. So the spec partitioning that was used is really around how do we align our specifications with kind of the architectural constructs that existed within NVMe. How do we take and make the core aspects of what really makes NVMe, some of the queues and command, like how we process commands, those types of things, and really make that the base of the specification. And then how you actually use the NVMe kind of base specification in terms of like what commands are supported and how a host interacts with that NVMe device. That is why we came up with the command set construct, and then how we communicate to the actual device, that is where the transports come from. And so we expect to add or to change command sets. We expect to add or change transports kind of independently of the base NVMe specification. And then that base specification piece is expected to apply to any command set or any transport that's used. So that was, in general, why we came up with the structure that we did.
For the next question, does the ZNS command set eliminate the flash transaction layer, and does the host then have to manage the NAND directly?
Right. I guess that's for me. This is an excellent question in that a ZNS SSD is very much like a conventional SSD today. What I mean by that is it does implement a flash translation layer. One of the key parts of ZNS is that while we expose kind of zones up to a host and you have to write sequentially, it the media management and reliability, the Uber like management of the drive continues to be within the SSD. So the only thing the host in general should have to think about is writing sequentially within a zone and reset it. So there is indeed a fastness layer within ZNS SSDs today, and the host should not have to manage kind of does not manage the media reliability in any other way than it does today with the conventional drives.
Thank you. Another question we received here is, can ZNS and key pair features coexist for the same device?
So this is Bill. I'll take that question. It's a great question. Part of this goes back to what Peter showed early on in terms of the fact that the command sets are per namespace. So a given namespace can only support one command set at any given time. But what that doesn't cover is the fact, as he showed, a single device may indeed support multiple command sets. So a single device could have a namespace that is a ZNS namespace and a separate namespace that is a key value namespace. So from a device point of view, you may indeed support both. As a matter of fact, we see some applications that have a significant value in supporting both, where they're writing certain things into a zoned namespace and other things that are object-oriented into a key value namespace. So a device can support both. It can support all three of the currently defined the three currently defined command sets: the NVM command set, the ZNS command set, and the key value command set.
Great, thank you for answering. Another audience member would like an answer to this question. They would like to know, a single namespace is formatted for a single specific command set, right?
So this is Bill. I think that's really kind of an extension of what I just covered, which is, that is correct. Any namespace is formatted and used for a specific command set.
I think let me just try to add a little bit of clarity, right? So namespaces are the thing. You format the namespace for the command set. You then attach namespaces to controllers. And if the controller is, provisioned to support those command sets, you can then interleave commands to those namespaces arbitrarily to the same controller.
Okay, thank you. And our next question here is, what drove NVM Express to support hard disk drives?
I think that, in the past, there were other storage technologies and people built their storage arrays and infrastructure around other storage technologies. As SSDs have grown in importance, people are now building their infrastructure around NVMe first. And there's a need to be able to plug in hard drives into this infrastructure. So we had a number of companies come into NVMe and ask for support for hard drives on NVMe. So that's what drove us.
Thank you. And for our next question here, for the key value command set, how do you expect SSDs to support in terms of byte granularity?
So this is Bill. That is kind of an under the covers question related to the device. The expectation is the device will allocate space. It will probably have unused space in the physical storage that fills out the additional bytes. But when the data is returned, because it knows the length of the key value pair, it will only return the number of bytes requested, the number of bytes associated with that key value pair. So while it may be stored on somewhat of a larger granularity, the data that is transferred either in a store or retrieve command would be based on a byte granularity.
Thank you. And our next question is, InfiniBand was not mentioned as a transport. Is it still supported?
Yeah, we lump that in under the RDMA transports.
Okay, great. And another question here is, from the application point of view, will it be practical to have different command set for different namespace with NVMe base command and ZNS command set? What is the practical pairs of key value to be implemented in an SSD? Can Samsung share some insight?
I'd like to take a stab at the first part. As we mentioned, there can be a namespace and it has a different command set. So the specification supports having two different namespaces with two different command sets. So this is very much supported, and it's all up to the implementation of the SSD. If you can format its media either with a zone namespace or a conventional namespace. I think maybe the second part of the question has always been answered, but I'll let up Bill if you want to add anything to the key value part.
So what was the second part of the question?
The second part of the question is, what is the practical pairs of key value to be implemented in an SSD?
The practical pairs. So practically, in terms of the what can be implemented in an SSD, implementing anything that goes up to the 32-byte key is definitely practical to implement. The value size, one of the limitations on what value size practically can be implemented is the fact that a key value pair is assumed to be an autonomous transaction. So it does become a matter of what amount of data can you autonomously write to the drive, which means that you can determine that either all of it was written or none of it was written. The practical limits today are probably up to the 1 to 10 gigabyte range, however.
All right, thank you for answering. Our next question is there any form of PI type of protection mechanism in a key value NS?
So there is, we have not prevented or prohibited that, but for the initial implementations of key value, we have not associated a protection information with that value. We believe that there's a lot more extensions that have to be done in order to provide protection to key value due to the size of the value, whereas in a logical block addressed system, you put protection information with each and every block, which is a fixed size. Now you need protection information that is capable of protecting something up into the gigabyte range.
Great, thank you. Another audience member would like to know, are we trying to map the NVMe spec to SAM? What are the new features we anticipate to be added with the evolution of IoT, 5G, and automotive use cases like autonomous vehicle for NVMe? Is there a need to look at different transport protocols than PCIe for those use cases?
I can briefly comment. I mean, so as I mentioned, we're in kind of the third phase of evolution of NVMe, where we are enhancing NVMe for new use cases and enhancing it based on things you can do with NVM that you weren't able to do with previous storage technologies or what didn't make sense. We have a bunch of work in flight. I can't really comment on what we will be rolling out in the future.
Okay, thanks, Peter. Our next question here is, in the earlier NVMe specs, we have NVM subsystem reset and controller resets. With the introduction of the domain terminology to the NVMe architecture, they're curious to know if any new reset types are defined for the domain.
That's a detailed question that's probably best, dug into the NVMe spec, but there is now the ability to reset a domain and not the whole subsystem. So yeah, that did affect those, that piece of NVMe.
Okay, thank you. Another question here is there an ecosystem available in Linux for key value pair command set namespace?
So there are There are drivers available for free on GitHub, available for implementing key value in Linux. It is stuff that Samsung has provided. There may be other drivers that other companies have provided for writing to key value devices.
Okay, and another audience member would like to know if the slide set can be downloaded. This will be recorded and published to the NVM Express YouTube channel. So yes, this will be available, and we do encourage you to share it with your colleagues. So that's the final question here. We don't have any more audience questions. It looks like we'll be wrapping up a bit early today. We really appreciate the presenters for providing their expertise here, and we hope this presentation helped our audience better understand the NVMe 2.0 specifications, refactoring, features, and command sets. And as I stated previously, this webinar recording will be available for viewing on demand on the NVM Express YouTube channel. And for more information, we encourage you to visit the NVM Express website at nvmexpress.org. And we would also like to take this opportunity to promote the upcoming UNH IOL webinar on October 20th at 1 p.m. Eastern Time. And this webinar will help you prepare for the upcoming NVMe and NVMe OF Virtual Plugfest number 16. And it will provide an overview of updates to NVMe interoperability and NVMe OF conformance testing, the mandatory tests required, and more. And you can register at the link provided on this slide. And with that, we will conclude today's webinar. And if NVM Express would like to offer a thank you to our presenters and also thank you to our audience participants, and we appreciate the lively Q&A.